So hi everyone, I'm Trishita, and today I'm going to be presenting our work on information flow control through modular model architecture. So this is going to be a four-part talk. The first part is going to be the motivation. So why do we need information flow control within machine learning? And then we're gonna formally describe the problem setup. After that, I am going to go over what our solution to this problem is, and then I will end with an evaluation of our proposed method. So first, I want to begin with a motivating scenario. Now imagine you're in a software engineering company where there's a bunch of different code repositories. You can see that they're color-coded. And then there's a bunch of different software engineers, and each engineer has access to a different subset of the code repositories, which is indicated by the access policies in the corner. Now, let's say you want to throw in AI into the mix, and you want to have a coding assistant, kind of like GitHub Copilot, that is trained on these code repositories and help these software engineers to write code. Now, the question here is that, how do we get this AI model to honor these access policies? And by that, I mean, how do we ensure that this AI model does not, to any given user or engineer, leak information from any code repository that that given engineer does not have access to? And so this is the main question that we are trying to target here. And quite literally, this is pretty impossible to do given how the current machine learning architecture is set up. And let me show you why. So this is what a traditional ML pipeline looks like. You have a giant training corpus that goes through a training pipeline and produces one single trained model. And then during inference, what the user does is they provide their input, which goes through an inference pipeline, goes to the model, and then you get the output. Now, there's two shortcomings with this approach. So the first shortcoming is that all of the training data is pretty much lumped together into one giant data set. And because of how that training is done, the second shortcoming is that during inference, there's just simply no way to provide an access policy to the model and get it to honor that access policy. So given a certain input, we have essentially no control over what the model is going to say in response to that input. So there's this lack of access control that is built into the way traditional pipelines work. And because of this, there is obviously, it can lead to inadvertent data leakage, as I'm sure many of you have seen in the news. So that was a very specific scenario, and we outlined many such other scenarios in our paper where issues like this might arise. But more generally speaking, what we are trying to solve is that, let's say you can divide your training data into non-overlapping partitions. And we call each partition a security domain. And each security domain contains data based on its sensitivity. So one security domain will contain data, one type of sensitivity, and so on and so forth. So let's say there's M of these security domains, and there's N different users. And each user, as described before, has a different access policy, which outlines which subset of these security domains that that user can access. Now, what we want, essentially, is a training pipeline and an inference pipeline such that when the user provides their particular input and access policy to the model can guarantee that the output of this model will only depend on the training data that that particular user's access policy allowed. So that is essentially the problem setup and the question we're trying to tackle here. Now, I'll go over what our proposed solution for this is, which we call parametric information flow control. So this solution has three essential aspects. The first aspect is isolation, which happens during training. And the idea of isolation is to separate the parameters that are influenced by each security domain. And to do this, what we do is we train separate experts that are independent of each other, one per security domain. And then we embed these experts into a larger model that is pre-trained on publicly accessible data. The second part of our solution is gating, which happens during inference. And so the idea of gating is that at runtime, the user will provide A, their input, and B, their access policy. And so using both of these, the model will then use the access policy to pick the experts that are accessible according to that access policy. And out of the accessible experts, it will shortlist a few experts that are actually useful for that particular input. Because not all accessible experts might pertain to the current input. So we want to shortlist further out of the accessible experts and pick out the ones that are actually useful for that input. So that is what happens during gating, which happens at inference. And then the final step to this process is aggregation, which also happens at inference after gating. So once we have shortlisted the accessible and relevant experts, what we need to do then is combine the information from these different experts to produce one final output for that given input for the user. And so the challenges of this kind of setup are the following. The first challenge is that the gating has to be real time. And there's many different reasons for this, but one of the biggest reasons is because we want to ensure strict information flow control. And so we cannot have any offline computations that select different experts based on certain input, because it has to be able to honor any given access policy at runtime. So it has to almost exclusively, the gating algorithm needs to almost exclusively select the experts at runtime. So very limited offline computation is possible in order to prevent leakage. Then the second part to this is scalability. Now we want this to be usable in like a decent sized scenario, and we want this to be able to scale to, let's say at least like hundreds to thousands of experts. And then the final point is modularity. So what we want our scenario to be is modular. So we want a solution where if you want to add or remove an expert or a security domain, you don't have to retrain the entire model. You can just remove that one expert or add that one expert and keep the rest of the model unchanged. And that will definitely help in scenarios where you have very, very large models with a lot of experts. So our solution, I'm going to go over the specific steps that I outlined. So the 3 steps, I'm going to go into a little more detail on each of these steps. So the first part is isolation. And as I said before, isolation involves just isolating the parameters that are influenced by each security domain during training. And so the way we do that is by independently training different experts, one for each security domain. And then once we have these experts, we embed these experts into a larger pre-trained model. Now, the key thing to note here is that since all of these experts are trained independently, the training can be done in parallel. And B, it also upholds modularity since all of the experts are independent of each other. If you remove or add a new expert, it won't affect any of the other experts or the larger model. So that is the isolation part. The next part I'm going to go over is gating, which is the idea of selecting A, accessible, and B, relevant experts during inference. And so we have 3 different ways to gate, and we envision that there's other multiple ways to do this, but we look at 3 in the paper, and over here I'm going to talk about one of them. So the way that we do gating in this particular algorithm, which is called pairwise gating, is the following. So the first thing we do is when the user provides input to the model, we vectorize this input, and then what we do is, since the user also provides their access policy, we use this access policy to filter out the experts that are inaccessible. And then we only keep the experts that are accessible. And then finally, we do this kind of similarity computation between the user's vectorized input and a vectorized version of all of the experts' training data, and compute which of the accessible experts are most relevant to this particular input. And we shortlist K out of the different accessible experts for this particular input. So that is how gating works, and this is how it looks like end to end. And then the final step to this is aggregation. And the idea of aggregation is to combine information from different shortlisted experts to produce one final output. So how we do this in two different ways. So one way to do this is once you have your K experts, you run the user's input through all K experts and then combine the output vectors at the end. So that is called output ensembling. The other way to approach this is through parameter ensembling, in which case what you do is instead of combining the outputs of the K experts, you just take the parameters of these K experts, combine the parameters and make one combined expert, run the user's input through this expert to get one final output. And this is the entire pipeline in all of its glory. It has all of the bells and whistles that I haven't gone over, but you can find this image in the paper. For evaluation, what we do is we test two different large language models, GPT-2 and OPT. We test it with two data sets. So one is PushShift, which is a Reddit data set, and we simulate security domains by dividing the data set based on the subreddit. So each subreddit was its own security domain. And we had 50 different subreddits, so 50 security domains. And then the second one was CodeParrot, which is another data set, and this was to simulate the scenario that I had in the introduction, where we basically took different GitHub repositories from 5 different languages, and each repository was its own security domain, and we had 82 of those. And we measured performance through Perplexity on the language modeling task, and we reported a % improvement on a pre-trained publicly available model. And then we also had a comparison with an insecure model that is trained on all of the security domains. So we had 2 baselines. And the results that we have show that we tested 500 different access policies for each of the different models. And we observed an improvement in Perplexity from 38 to 62% compared to the pre-trained only model. And if we run the experts in parallel, we also can achieve a very minimal performance degradation in terms of runtime compared to a model without this architecture of only 1.9% overhead. And we have a lot more results on testing different effects of different gating algorithms, different aggregation schemes, et cetera, in the paper. And I would encourage you to take a look at that. And that is the QR code of the paper, and I am open to any questions.